Hello everyone. In this video, I will be discussing our CVPR paper named Divide and Conquer, answering questions with object factorization and compositional reasoning. While we interact with about hundreds of objects on a daily basis, each of them can have millions of appearances, depending on the light conditioning, different viewpoints, and the shift of fine-grained attributes. To accommodate the complexity of the visual world, it is of significance to develop the ability to factorize these objects and correlate them based on their commonality. Aiming to enhance the generalizability and the interpretability of visual reasoning model, our study focuses on incorporating the elements of compositionality. In particular, our model centers around the compositionality of objects and reasoning process. We learn a collection of discriminated prototypes to factorize objects into finer bases, denoting various semantics such as their supercategory, color, and shapes. Then, we incorporate this prototype within an explicit reasoning process, where each step is instantiated with a distinct neural module. The neural modules are dynamically combined together to formulate the decision-making process and the network for answering different questions. In this way, we are able to bridge a variety of objects based on their commonality on the semantic space and benefits from structured reasoning. Our method consists of two major components. The first one is an object factorization method for automatically deriving discriminated prototype. The principal idea behind our method is to project the implicit object features onto trainable prototype by measuring their similarity. And then we will use the weighted combination of the prototype to classify those objects, where the weights are the computed similarity. In this way, we are able to represent a variety of objects within a common space formulated by the prototype. Note that here, we consider the multi-label object recognition task where multiple objects appear together in the same images, which will facilitate the correlation between diverse objects. In addition, to ease the requirements on expensive instant-level annotation, we also leverage an attention mechanism to convert the instant-level prediction into image-level predictions by spatially aggregating them. Upon deriving the prototype, we then develop a novel neural module network for reasoning. As we can see in the figure, each module is responsible for distinct operations, such as find, relate, and describe, and they will output an attention map which encode both the important regions for the previous reasoning step and the regions of interest for the current operation. The attention map will be iteratively updated and used at the end to collect the visual information for deriving the answer. Different from conventional neural module network, which relies on implicit features, our method directly uses the similarity between the visual observations and prototype for decision-making. As a result, even though the model may not have seen an object category before in the training data, it can still reason with it by correlating it with other non-objects on the space formulated by the prototypes. Moreover, we also propose a semantic memory module, which accumulates important prototypes attended over time and facilitates integral reasoning throughout the complete decision-making process. Our results show that the proposed method is able to learn a wide range of prototypes. Some prototypes encode low-level visual cues, such as the round shape, the jagged pattern, and strips, while others focus more on high-level semantics, such as different types of views and objects displaying text. In addition, we can also cluster different objects based on their similarity with prototypes. As shown in the table, the objects are well separated based on their contextual relationship. For instance, group 1 and 2 are about objects belonging to similar supercategories, such as drink and kitchenware, while groups 3 and 4 are more about the appearance in visual scenes, such as baseball game and bedroom. In terms of groups 5 and 6, they are objects sharing similar characteristics, such as objects related to text and scenery. Note that here we only show part of the result, and in total we have over 700 objects clustered in 30 groups. For comprehensive evaluation of the reasoning capability of our method, we consider two different settings. For the first setting, we consider visual question answering with known or novel objects, where the novel objects do not appear in both the images and the questions within the training data. The result shows that our approach is more advantageous compared to the state-of-the-art, especially on questions with novel objects. For the second setting, we are interested in evaluating the robustness against data biases. For this, we opt to evaluate without distribution questions. Results show that our method is also useful in generalizing towards different data distribution. In addition to improving the reasoning capability, our approach also offers an interpretable interface for understanding the rationale behind answers. Specifically, it can interpret the visual observation based on the matched prototype and their representative images. In the first example, the model successfully correlates the attended apple with prototypes for different fruits in the select step. Then it focuses on prototype denoting brown color for the filter step. In the second example, women is a novel object unseen in the training data. Nevertheless, the model is still able to localize it based on the commonality of clothing between men and women. Our approach can also visualize the reasoning process with a combination of reasoning steps, which can be particularly useful for understanding how models arrive at the final answer. For more details of our method, please visit the project page and come to our poster presentation section. Thank you.